What if the most foundational story ever told, the story of our own cosmic origins, begins not with a word but with an impossible silence? What if the overture to everything we are, to every sun and every world, was a period of darkness so absolute, so profound, that it held the entire universe in a state of suspended animation? This is the paradox that lies at the very heart of creation. We imagine the beginning as a cataclysm of light, an explosion of infinite energy, and in one sense we are right. Our universe was born in a furnace of unimaginable ferocity, a point of infinite density and heat that erupted into existence. In the first picoseconds there was no matter as we know it, only a seething incandescent quark-gluon plasma, a symphony of pure energy, where the laws of physics were still being forged. As this primordial fireball expanded at a rate that defies all earthly comparison, it began to cool. Energy congealed into the first subatomic particles, the building blocks of reality, which then coalesced into the simplest elements, hydrogen and helium. For 380,000 years, this infant cosmos was a brilliant, blinding fog. It was a chaotic soup of charged particles, protons, electrons, and photons of light, all locked in an intricate dance. Light could not travel freely. Every photon was instantly scattered by a free electron trapped like a firefly in a jar, its journey ending before it truly began. The entire universe was opaque, a glowing, impenetrable wall of its own making. Then a moment of profound transformation occurred. The universe, in its relentless expansion, cooled enough for the frantic dance to end. Electrons finally losing their fiery energy were captured by protons forming the first stable neutral atoms. This event, which we call recombination, was the single greatest act of clarification in cosmic history. For the first time, light was set free. The photons that had been ricocheting wildly for millennia were suddenly liberated, released to stream unimpeded across the cosmos. This is the oldest light we can see, the faint residual glow of creation itself, a light now stretched by cosmic expansion into the microwave part of the spectrum. It is the cosmic microwave background, the universe's first baby picture, a faint echo of the fires of its birth. It tells us of a universe that was almost impossibly smooth, yet tattooed with minuscule fluctuations in temperature, the faint whispers of a structure yet to come. This ancient light has been our Rosetta Stone, allowing us to decode the age, composition and geometry of the cosmos with breathtaking precision. But it is also a barrier. It is the edge of our vision, a wall of light beyond which we cannot directly see. It is the final fading snapshot of the hot, dense early universe. And as this light streamed away, as the last echo of the Big Bang faded into the invisible, the universe underwent a staggering change. It became transparent, yet there was nothing to see. The cosmic stage was set, the curtain had lifted, but the actors had not yet arrived. The universe plunged into darkness, a true, piercing and absolute darkness that would last for hundreds of millions of years. This was not the darkness of a moonless night on Earth, punctuated by the distant glow of stars. This was a primordial night, an utter void of luminescence, for not a single star had yet been born. The great age of light had ended, and what followed was an epoch so mysterious, so devoid of known events, that we have given it a name that evokes both its nature and our own long-standing ignorance, the cosmic dark ages. Imagine it. A universe filled with a silent, featureless fog of neutral hydrogen and helium gas, stretching for unimaginable distances in every direction. There were no galaxies to pinwheel through the void, no nebulae to blaze with the colours of creation, no supernovae to tear through the fabric of space with elemental fury. The only sound was the deep, sub-audible hum of space-time itself, continuing its inexorable expansion. The only motion was the slow, patient, and utterly invisible work of gravity. This was the universe holding its breath, a vast, dark, and cold nursery waiting for a spark. The raw materials were all there, a cosmic ocean of hydrogen, but the recipe for igniting them into suns was a process that would take an almost unimaginable amount of time, unfolding in the deepest blackness. For generations of astronomers, this era was a complete blank, a lost chapter in our cosmic story. We could see the evidence of the Big Bang in the cosmic microwave background, and we could see the brilliant galaxies of the later universe through our telescopes, but the immense gap between them was a realm of pure theory and speculation. It was a dark room we knew we had to cross to get from the beginning to now, but the nature of the room itself was a mystery. Within that suffocating darkness, however, the most important work in the history of the cosmos was underway. Those tiny, almost imperceptible density fluctuations we see imprinted on the universe's first light were the seeds of everything to come. They were the ghost in the machine. In the places where the primordial gas was infinitesimally denser, gravity, the patient and relentless architect of the cosmos, began its silent work. It was a force acting on a scale and over a time scale that dwarf human comprehension. An extra atom here, a slightly thicker wisp of hydrogen there, these were the gravitational anchors around which the future would be built. Over millions of years, these anchors pulled more and more material toward them. Invisible rivers of dark matter, the mysterious scaffolding of the cosmos, formed vast interconnected filaments, creating a cosmic web. The hydrogen and helium gas, the ordinary matter we know, was drawn into these filaments, trickling down into the deepest gravitational wells, the nodes where the filaments crossed. Slowly, painstakingly, clouds of this primordial gas began to form. At first, they were just diffuse cold gatherings in the dark, but as gravity squeezed them, they grew denser and hotter. The pressure at the core of these collapsing clouds mounted an alchemical process playing out in the void. For millions of years, the universe remained dark as these protostars gathered mass, their cores growing ever hotter, ever more compressed. This was the great question, the central enigma that has haunted cosmology for a century. How did this process happen? What were these first stars, these so-called population 3 stars actually? Like, our models suggested they must have been titans, monsters of pure hydrogen and helium, hundreds, perhaps even thousands of times more massive than our own sun. Living fast and dying young, they would have been celestial blowtorches burning with a ferocious intensity that we can barely imagine. Their light would have been the first to pierce the cosmic gloom, the first beacons in an endless night. And their explosive deaths would have been the forges that created the first heavy elements, carbon, oxygen, iron, the very elements that make planets and life possible. They were not just the first lights, they were the architects of chemical complexity, the ancestors of every subsequent generation of stars, including our own. They were the ones who began the process of reionization, their powerful radiation ripping electrons from the neutral hydrogen fog and piece by piece making the universe transparent and luminous once more. These first stars would not have been alone for long. Pulled together by their mutual gravity, they would have formed the kernels of the first galaxies, fragile infant collections of light, battling against the overwhelming darkness. These were the true pioneers, the city builders of the cosmos, establishing the first small footholds of structure and order in a universe that was still largely empty and chaotic. Finding them, however, has been the observational equivalent of searching for a single candle flame in a fog-bound abyss from billions of light-years away. The light from these first objects, even if we could detect it, has been travelling toward us for over 13 billion years. And during that immense journey, the expansion of the universe itself has stretched it, shifting it from the visible and ultraviolet light in which it was born, all the way down the electromagnetic spectrum into the infrared. To our eyes, and to the eyes of telescopes like Hubble, this light is completely invisible. It is a ghost from a time we could only dream of seeing. For all of human history, the cosmic dark ages remained sealed, its secrets locked away by distance time and the very laws of physics. We had the beginning of the story, and we had the story from the first billion years onward, but the crucial transformative chapter, the one that explained how the universe truly woke up, was missing. We were like archaeologists who had found the blueprints of a great cathedral, and the cathedral itself, but had no idea how the first stone was ever laid. This is where our story pivots, because that lost chapter is now finally being written. And the instrument of this revelation is not merely an improvement on what has come before, it is a paradigm shift in our ability to perceive reality. It is a machine designed specifically to hunt for these ghosts, to see this invisible, time-stretched light from the edge of creation. Floating 1,000,000 miles from Earth, its magnificent golden mirrors cooled to just a few degrees above absolute zero, the James Webb Space Telescope is more than an observatory. It is a time machine. It is an archaeologist of light meticulously sifting through the oldest photons in the universe to uncover the foundations of the cosmos. Its singular purpose is to stare into that primordial darkness and find the first sparks of dawn. It was built to answer the very questions that have defined the limits of our knowledge. When did the first stars ignite? How did the first black holes form and grow into the supermassive behemoths that anchor galaxies today? How did those first fragile star clusters assemble themselves into the majestic spiral and elliptical galaxies that populate our modern universe? For the first time in human history, we are no longer guessing. We are not just refining our theories, we are witnessing the events themselves. The data now streaming back to Earth from JWST is not an iteration, it is a revolution. The story we thought we knew is being torn up and rewritten in real time. The first pages of this new cosmic genesis tell a tale far richer, far stranger, and far more spectacular than we ever dared to imagine. The universe, it seems, did not wake up slowly. It burst into a complex and brilliant existence with a speed and maturity that is forcing us to rethink everything we thought we knew about the dawn of time. The cosmic dark ages are over, not just in the ancient universe, but for us, the explorers who have so long stared into that abyss. The great silence is about to be broken, and the secrets hidden for 13 billion years are at last coming into the light. What if the most brilliant, most violent explosion in all of existence gave birth to darkness? How could an event that contained all the energy that would ever be a fireball of creation, so incandescent it defies imagination, led not to an age of eternal light, but to a profound universe-spanning night? This is one of the great unsettling paradoxes in the story of our cosmos. To understand it, we must journey back beyond the familiar tapestry of stars and galaxies, past the swirling nebulae and glittering clusters, to a time when the universe itself was still an infant. We've seen the afterglow of its birth, the fading echo of that first great fire imprinted on the heavens as the cosmic microwave background. That relic light tells us of a universe impossibly hot, a seething, chaotic plasma, where the fundamental particles of matter and energy were locked in a frantic dance. Imagine trying to look through the heart of a star. You would see nothing but a blinding uniform glare, like the universe's great messenger was effectively trapped ricocheting endlessly off free-roaming electrons, unable to travel more than a few moments before being scattered in a new direction. The cosmos was luminous, yet it was utterly opaque. It was a kingdom of light without a single viewpoint. But the universe had one relentless overarching command: expand. And with expansion came cooling. With every passing moment, the fabric of space-time stretched, pulling everything further apart, diluting that primordial heat across an ever-growing volume. For 380,000 years, this cooling continued, a slow cosmic exhalation. The frantic energy of the newborn universe began to subside its fever-breaking degree by imperceptible degree until it reached a critical magical threshold. A temperature of roughly 3,000 degrees Kelvin. This may sound incredibly hot to us, but for the early universe it was the dawn of a new kind of autumn. It was now cool enough for the relentless attraction between positive and negative to finally win. For the first time, the positively charged protons, the hearts of future atoms, could capture and hold the negatively charged electrons that had run wild for millennia. In a sweeping cosmos-wide event cosmologists call Recombination, the first stable electrically neutral atoms were forged from the fire, not the complex elements of our world, but the simplest of all hydrogen and helium. The fog lifted. With the electrons now bound into atoms, the photons of light, the ancient messengers from the Big Bang, were suddenly liberated. Their frantic pinball journey was over. For the very first time, the universe became transparent. The light from that moment, now free to race across space-time unimpeded, is what we detect today as the cosmic microwave background. It is the oldest photograph possible, the universe's own baby picture. And here at the moment of ultimate clarification is where the paradox deepens. The very act that cleared the cosmic air also turned out the lights. The source of that brilliant opaque glare, the superheated plasma itself, was gone, consumed in the creation of neutral gas. What replaced it was a placid, featureless expanse of hydrogen and helium atoms, and neutral hydrogen gas on its own does not shine. The universe was now see-through, but there was nothing to see. No stars, no galaxies, no light. This was the beginning of the cosmic dark ages, a vast silent epoch, a chapter in our universe's story that was almost entirely blank. It was an interregnum between the fading glow of creation's fire and the first spark of stellar dawn. Try to imagine it to place yourself within that primordial blackness. The silence would be absolute, a quiet so profound it is beyond human conception. There is no sound in the vacuum of space, but this was a deeper stillness, a lack of cosmic activity of event. The only motion was the slow, inexorable expansion of space-time itself, and the even slower, almost imperceptible pull of gravity. The darkness would be nearly perfect, a velvet blackness stretching to every horizon because there were no horizons. You were simply adrift in an endless starless night. The only light remaining was the ghost of the Big Bang's afterglow, that newly freed cosmic microwave background. But as the universe continued to expand, this light was stretched, its waves pulled longer and longer, shifting from the brilliant yellow-white of a searing plasma, down through orange, past red, and into the invisible domains of infrared and microwave. To any observer living in that time, the sky would have grown progressively dimmer, the last embers of creation fading slowly into an imperceptible cold background hum. It was a universe of profound simplicity. Just three things existed on the grander scales. There was the ordinary matter, the newly formed atoms of hydrogen and helium, a diffuse, evenly spread mist. There was the radiation, that fading echo of the Big Bang. And then there was the invisible actor, the puppet master, waiting in the wing's dark matter. This mysterious, unseen substance, which had been present since the beginning, didn't interact with light at all. It felt gravity, and only gravity. And during the chaos of the plasma age, it had already begun to quietly shape the cosmos. While the plasma was being pushed around by the pressure of its own light, the dark matter was free to collapse under its own weight. It had already started to form vast invisible structures, a sort of cosmic scaffolding, a ghostly network of filaments and massive halos spreading throughout the universe. And now, with the plasma neutralized into calm, tractable gas, this invisible architecture could finally begin its work. The Dark Ages were not a time of true stasis. They were a time of quiet, patient construction performed in the dark. Imagine a vast, dark ocean. The hydrogen gas was the water, almost perfectly smooth. But beneath the surface, the invisible topography of dark matter halos created gravitational valleys and depressions. Slowly, inexorably, atom by atom, the hydrogen gas began to feel this subtle pull. It began to drift, to flow into these unseen gravitational reservoirs, a process so gradual it would take hundreds of millions of years to show any visible effect. This was the unseen drama of the Dark Ages, a silent symphony of gravity playing out on a stage of absolute black. The universe was gathering its breath. It was concentrating its resources, pulling the raw fuel for the first stars and galaxies into the places where they would one day ignite. It was a cosmic winter where the seeds of future spring were being sown deep underground in the fertile soil of dark matter halos. This period, this great unglowing, lasted for an almost unimaginable stretch of time. It began 380,000 years after the Big Bang, and it continued for, well, we didn't know for sure. Perhaps 100 million years. Perhaps 300 or 400 million years. The precise end date was one of cosmology's greatest mysteries. An entire era, a foundational chapter of cosmic evolution that accounts for a significant fraction of the universe's youth, was a complete and total blank to us. For astronomers, this presented a profound and tantalizing problem. It was like being a historian with a magnificent detailed library covering all of world history, but with the very first most important chapter, the one that explains how civilization began, physically ripped out of every book. Our telescope's marvels of human ingenuity, like the Hubble Space Telescope, had pushed our vision back to incredible distances, to times when the universe was just a fraction of its current age. Hubble showed us nascent galaxies, chaotic and beautiful as they were over 13 billion years ago. It saw the universe when it was a toddler taking its first dynamic steps. But Hubble, and every telescope like it, has a fundamental limitation. They are passive instruments, they need light to see. You cannot take a photograph of a pitch-black room and expect to see the furniture inside. Hubble could look in the direction of the Dark Ages, but all it could see was nothing. An absence. It could not pierce that veil of time because there was no light coming from behind it. The cosmic microwave background was the wall at its back, the first page. The most distant galaxies Hubble could see were the start of the next chapter. The story in between the story of how the universe went from a smooth dark gas to a brilliant tapestry of stars was entirely lost to observation. It existed only in our theories, in the elegant equations of cosmologists and the complex supercomputer simulations that tried to model that unseen era. Our simulations told us a magnificent story. They showed us those dark matter halos growing, their gravitational grip tightening. They predicted that within the densest, most massive of these halos, the hydrogen gas would be compressed beyond a critical point. Gravity would overwhelm the gas's internal pressure, triggering a runaway collapse. Temperatures and pressures in the core of these collapsing clouds would skyrocket, rising to millions of degrees until a new kind of fire was ignited. Nuclear fusion. The first star. The simulation suggested these firstborn stars would be unlike anything in the universe today. Forged from pure, pristine hydrogen and helium, untainted by the heavier elements cooked up in later stellar generations, they would have grown to gargantuan proportions, perhaps hundreds of times more massive than our own Sun. Because of their immense mass, they would burn with a ferocity we can barely comprehend, shining with the light of a million suns, emitting a torrent of high-energy, ultraviolet radiation. They would be celestial blowtorches, living fast and dying young, exploding in titanic supernovae after only a few million years. But in their short, spectacular lives, they would change everything. Their light would be the first to ever pierce the darkness of the cosmic dark ages. One by one, then in clusters, then in the hearts of the first protogalaxies, these stellar pioneers would set the universe ablaze. This predicted moment was called Cosmic Dawn, the end of the long night. This was the event we were desperate to witness. Not just to find a more distant galaxy, but to see the very first light that was not a relic of the Big Bang. To witness the moment the universe created its own new light. But how could we possibly see it? Even if we could build a telescope powerful enough, we faced another cosmic hurdle, the universe's relentless expansion. The light from those first brilliant blue-hot stars would have begun its journey to us over 13.5 billion years ago, and for all that time as it crossed the cosmos, the very fabric of space it travelled through would have been stretching. This stretching would pull on the light waves, lengthening them, robbing them of their energy. The intense high-energy ultraviolet light would be stretched down through the visible spectrum past blue, past yellow, past red, and all the way into the invisible realm of the infrared. It is an effect known as cosmological redshift, and the further back we look, the more extreme the redshift becomes. The light from cosmic dawn would be so stretched, so redshifted, that by the time it reached our modern telescopes it would arrive as a faint ethereal whisper of long wavelength infrared radiation. Hubble's magnificent eye is primarily tuned to visible and ultraviolet light, with only a narrow window into the near-infrared. It was fundamentally blind to the spectral colours of cosmic dawn. It was like trying to hear an impossibly deep bass note with ears that can only register a soprano's high C. The information was there, streaming past us, bathing our planet every second. A ghost light from the edge of time carrying the story of the first stars. But we had no way to see it. The challenge was laid bare. If we ever wanted to fill in that missing chapter of cosmic history, if we truly wanted to witness the moment darkness gave way to light, we couldn't just build a better version of Hubble. We had to build an entirely new kind of eye, a machine designed to perceive the invisible. It would need to be the largest space telescope ever conceived, with a mirror of unprecedented size to collect every possible photon of that faint ancient light. It would need to be cryogenically cold, chilled to near absolute zero so its own heat wouldn't blind it to the faint warmth of its cosmic targets. And it would have to be sent far from Earth beyond the obscuring glow of our own planet and the moon to a lonely stable point in deep space. It was a technological challenge on a scale never before attempted. A dream that would take decades, and the minds of thousands to even begin to realise. We had to invent a time machine not to travel through time ourselves, but to allow the light from the universe's most pivotal moment to finally complete its journey and tell its tale. We needed a successor. We needed an infrared sentinel. We needed the James Webb Space Telescope. And so in the silent waiting dark a change began. It was not a sudden flash, not a singular universe-spanning event. It was something slower, more insidious, more profound, a creeping transformation happening first in isolated pockets, then in growing, overlapping spheres of influence. The first sparks in the dark began to do more than just shine. They began to fight back against the very fabric of the cosmos, against the oppressive neutral hydrogen fog that had defined existence for hundreds of millions of years. This was not a gentle sunrise. It was a war for the soul of the universe, and the prize was transparency. This was the beginning of the epoch of Reionization. To understand its monumental significance, you have to remember the state of that primordial cosmos we left behind. It was a universe you could not see through. A universe where a beam of light, no matter how powerful, would travel only a short distance before it was snagged, absorbed by a neutral hydrogen atom, its journey ending abruptly. The cosmos was opaque, a boundless, featureless grey mist. For the universe to become the one we know, filled with glittering galaxies separated by vast empty see-through voids, that mist had to be cleared. The hydrogen had to be fundamentally altered. The process was one of beautiful, violent physics. An atom of neutral hydrogen is simple, one proton, one electron. Bound together, they are experts at absorbing certain frequencies of light. But hit that atom with a sufficiently energetic photon, a particle of ultraviolet light, with enough of a punch, and you can knock the electron clean off. The atom is no longer neutral, it is ionized, a lone proton. An ionized universe is a transparent universe. It's a cosmos where light once freed can travel unimpeded, for billions of years, carrying its ancient stories all the way to our telescopes. Reionization was the universe-wide metamorphosis from a closed, claustrophobic state to an open, liberated one. It was the single greatest environmental change in cosmic history. Herein lies the central mystery that haunted cosmologists for decades. What could possibly wield that kind of power? What could produce a flood of high-energy radiation so immense, so pervasive, that it could systematically strip the electron from nearly every single atom in the entire vast expanse of the cosmos? The scale of the challenge is almost impossible to comprehend. It would require more than a few scattered lights. It would demand a legion of celestial blowtorches working relentlessly for hundreds of millions of years, burning away a fog of unimaginable proportions. The hunt was on for the architects of transparency, the ionizers of the cosmos. And in the shadowy realm of theoretical physics, three primary suspects emerged. Our first and perhaps most mythic suspect is a true titan, the so-called Population 3 star. These were not stars like our Sun. They were not even like the brilliant blue giants we see in nebulae today. They were monsters. Primordial beasts forged only from the raw material left over from the Big Bang itself, pure hydrogen and helium. Today, every star, including our own, is seasoned with heavier elements. Carbon, oxygen, iron, forged in the hearts of previous generations. These elements act as cooling agents, allowing gas clouds to collapse more slowly and form smaller, more stable stars. But the first stars had no such inheritance. They were born from pristine, unpolluted gas. Without those heavy elements to help radiate away heat, the collapsing primordial clouds just got hotter and hotter, resisting gravity's pull until they reached truly colossal masses. We're talking about stars that were potentially hundreds, maybe even 1,000 times more massive than our Sun. They were not just stars, they were elemental forges of terrifying intensity. Their cores burned at temperatures we can barely model, fusing hydrogen into helium at a furious, unsustainable rate. Because of this immense mass and heat, they were searingly bright, shining with the light of millions of our suns combined. More importantly, their surfaces were so hot that they pumped out an unbelievable torrent of high-energy ultraviolet radiation. They were the perfect machines for the job of reionization. A single Population 3 star could in theory ionize a vast bubble of hydrogen around it, carving out a pocket of clarity in the cosmic murk. As more and more of these behemoths ignited across the cosmos, their individual bubbles would begin to overlap to merge, creating ever larger regions of transparency, like holes melting in a great sheet of ice. Yet there is a ghostliness to this beautiful theory. Their very power was their doom. These stars lived fast and died young. While our Sun will live for 10 billion years, a population 3 star would burn through its entire fuel supply in a mere 2 or 3 million. They existed for a cosmic blink of an eye, before exploding as magnificent supernovae, seeding the universe with the first heavy elements and paving the way for the next generation of stars, population 2. They were the ultimate pioneers. They lived. They transformed the cosmos, and then they vanished utterly, leaving no direct trace. For decades they have existed only in our supercomputer simulations, necessary phantoms required to explain the world that came after them. We had never seen one. We had no direct proof they even existed. They were a powerful but unsubstantiated suspect. If the population 3 stars were the universe's brute force pioneers, our second suspect represents a more centralized, almost sinister form of power, the quasar. At the heart of this suspect is not a star, but a black hole. Not the kind of stellar mass black hole left behind by a dying star, but a supermassive black hole millions or even billions of times the mass of our Sun. Today these gravitational tyrants sit quietly at the center of most large galaxies, including our own. But in the early universe the environment was different. It was target-rich. Vast streams of gas, entire nebulae, and nascent star clusters were funneled toward the galactic core, drawn into a gravitational whirlpool from which there was no escape. This infalling material did not go quietly. It formed a swirling, superheated structure around the black hole called an accretion disk. As gas and dust spiraled inward, friction and tidal forces heated it to millions of degrees, causing it to blaze with a light that could outshine its entire host galaxy by a factor of 1,000. This is a quasar, a gravitational engine of unimaginable efficiency, converting mass into pure energy with a ferocity that dwarfs nuclear fusion. And like the population 3 stars, quasars are prodigious producers of the very high-energy photons needed to ionize hydrogen. They were cosmic lighthouses, their beams capable of punching through the fog and clearing out enormous volumes of intergalactic space. The appeal of this theory was its sheer power. You wouldn't need as many culprits. A relatively small number of active quasars strategically located could potentially do the work of millions of stars. They were the ultimate ionizers, celestial blowtorches of galactic scale. But this theory came with its own profound timeline-shattering paradox. How did such massive black holes get so big so fast? The standard model of black hole growth is a slow, steady process of accretion and mergers. To grow a billion solar mass black hole in just a few 100 million years after the Big Bang is like trying to explain a full-grown oak tree appearing just a week after planting the seed. It seemed to break the rules of cosmic growth. This led to more exotic theories. Perhaps primordial black holes were formed directly from the dense plasma of the Big Bang itself, bypassing the need for a star altogether. Or maybe colossal clouds of gas collapsed directly into massive black holes, seeding the first galaxies with gravitational monsters from birth. Whatever the mechanism, the timeline was a problem. Finding a quasar shining brightly just 700 million years after the beginning was like finding a fossil in a layer of rock where it simply shouldn't exist. Quasars were an incredibly effective suspect, but one with a deeply questionable backstory. Their presence in the early universe was an enigma in itself, a puzzle wrapped inside the larger mystery of Reionization. This brought cosmologists to the third and perhaps most democratic possibility. What if the clearing of the fog wasn't the work of a few mythic heroes or a handful of powerful tyrants? What if it was the result of a popular uprising? The third suspect is not a single object, but a swarm, the first dwarf galaxies. These were not the majestic structured spirals we see today. They were messy, chaotic, clumpy collections of gas and dust and stars 100 times smaller than our Milky Way. Individually they were insignificant, their light a mere flicker in the oppressive dark. But their strength was in their numbers. Simulations predicted that the early universe should have been teeming with them. Countless tiny galaxies, each undergoing furious bursts of star formation. Inside each one, thousands or millions of hot young blue stars, the more normal population 2 variety, were still blasting out a substantial amount of ionizing ultraviolet light. The theory was simple death by 1,000 cuts. No single dwarf galaxy could clear a large region of the cosmos on its own, but the combined overlapping effort of billions of them, a chorus of 1 billion stellar voices singing in unison, could collectively produce enough radiation to get the job done. It was a slow, grassroots effort, reionization from the bottom up. This felt in many ways like the most plausible scenario. It didn't rely on mythic unseen stars or black holes that seemed to defy their own formation timeline. It used objects that we knew had to exist in large numbers. But this swarm theory faced its own critical and potentially fatal flaw, the escape problem. A dwarf galaxy is a very busy, very crowded place. It's full of the same neutral gas and dust that constituted the cosmic fog. The very photons needed to reionize the universe outside the galaxy first had to escape the galaxy of their birth, and it was entirely possible that they couldn't. Imagine lighting a candle inside a thick frosted glass box. The light is there, but it can't get out to illuminate the room. Many models suggested that these early galaxies were too opaque, too enshrouded in their own gas for a significant fraction of their ionizing photons to ever reach intergalactic space. The radiation would be absorbed by the galaxy's own hydrogen before it ever had a chance to contribute to the Great Clearing. The revolution might have been confined within its own borders. For this theory to work, the first galaxies needed to be leaky, full of holes and channels cleared by supernovae, allowing the radiation to stream out into the void. Whether they were leaky enough remained one of the biggest question marks hanging over the entire epoch. So there we stood for decades at a cosmic crossroads. 3 compelling suspects, each with a strong motive and method, but each with a frustrating, debilitating flaw in their story. Was it the Titans, the ghosts of Population 3, who vanished after their heroic work? Was it the behemoths, the impossibly early quasars that shone with borrowed gravitational light? Or was it the swarm, the collective murmur of 1 billion dwarf galaxies, whose true power depended on their ability to let their voices be heard? The truth could very well be a complex combination of all 3, a grand conspiracy where different culprits dominated different stages of the process. Perhaps the first stars started the job punching the initial holes only for galaxies, and a few opportune quasars to finish it. We had become cosmic detectives piecing together a crime scene that was 13 billion years old and universe-wide. And we weren't without our clues. By studying the light from the most distant known quasars, astronomers had found a crucial piece of forensic evidence. They could see how that light was absorbed by the hydrogen it passed through on its long journey to Earth. And in the spectra of the most ancient of these objects, they found a feature known as the Gunn-Peterson trough. It was in essence a wall of darkness, a clear signal that, at a certain point in the past, the light was travelling through a universe that was still largely opaque, still filled with that neutral fog. This incredible clue gave us a time frame. It told us that the process of reionization was largely complete by the time the universe was about 1 billion years old. It was like finding the victim, and knowing the time of death a monumental achievement in itself. But we still didn't have the murder weapon. We couldn't see the culprits in the act. The Gunn-Peterson trough was the shadow, the after-image of the fog, not a picture of the fire that burned it away. We were stuck staring at the edges of the mystery. Our best models, our most powerful supercomputers, could only produce plausible screenplays of what might have happened. We could direct the film, but we had never seen the actors. The entire grand narrative of our cosmic origin story from the darkness to the light hinged on this enigmatic chapter. A chapter for which we had no direct observations, no definitive proof. The dawn of the cosmos, the most transformative event since the Big Bang, was hidden from us, shrouded in the mists of time. To solve it, we would need more than theory. We would need more than simulations. We would need a time machine. We would need a new eye powerful enough to stare back across the void and into the heart of that ancient twilight, to catch the very first sparks in the act of setting the universe ablaze. An observatory was being conceived, a golden mirror designed for one ultimate purpose: to witness the dawn and finally bring our ghosts into the light. And so the promise forged over decades of labour and yearning was finally carried to the edge of the abyss, to a launch pad in French Guiana. Here, folded within the nose cone of an Ariane 5 rocket, lay the most complex and powerful eye we have ever conceived. This wasn't merely a machine awaiting its ascent. It was a vessel carrying the accumulated hopes of a generation of scientists, the answer to questions we'd scarcely dared to whisper. For every single person who had worked on the James Webb Space Telescope, this moment was the terrifying, breathtaking culmination of a life's work. The cost, not just in treasure, but in human dedication, was astronomical. A single catastrophic failure at this stage would mean more than a lost mission. It would be a dream dissolving into fire and smoke against the blue sky. The final countdown was not a sequence of numbers, but a litany of prayers muttered in control rooms from Kourou to Baltimore to Houston. You could feel the planet holding its collective breath. Then ignition. A pillar of controlled fire, a force of unimaginable violence, began to push against the immense inertia of Earth's gravity. The roar was the sound of humanity refusing to be confined of our relentless drive to know what lies beyond the horizon. Slowly at first, then with gathering inexorable speed, the rocket climbed a 300-ton prayer aimed at the heavens. It ascended through the atmosphere, a brilliant torch against the encroaching darkness, carrying its precious cargo toward the silent, unforgiving vacuum of space. For 27 minutes of sheer, unadulterated terror and hope, we watched a single point of light, our proxy, our emissary to the early universe, as it fought its way free from the world that built it. And then, separation. The telescope was on its way, a solitary traveller now beginning a month-long 1.5 million-kilometre journey to a unique point of gravitational stability known as the second Lagrange point, or SL2. This was not a destination of convenience. It was a place of profound cold and darkness, far from the interfering glare of the Earth and Moon, a place where the telescope's sensitive instruments could cool to just a few degrees above absolute zero, the cryogenic temperatures required to detect the faint ancient heat of the first stars. But the journey was only the first ordeal. The true trial, the sequence that kept engineers awake for years, was yet to come. JWST had been launched as a compressed, tightly folded marvel of engineering, a cosmic origami butterfly tucked into its chrysalis. To become the magnificent observatory it was designed to be, it had to perform the most complex deployment sequence ever attempted in space. Hundreds of individual steps, each one a potential mission-ending point of failure, had to execute perfectly in sequence, with no possibility of a human repair mission. This was a ballet of motors, hinges and latches performed in total silence 1 million kilometres from home. The first and most harrowing was the unfurling of the sunshield. 5 layers of a gossamer-thin material called Captain, each one thinner than a human hair, had to be meticulously pulled taut by a system of cables and pulleys. This tennis court-sized shield was Webb's parasol, its refrigerator designed to block the light and heat from the sun, earth and moon, creating a shadowed environment of almost unimaginable cold on one side, while the other side baked at over 85 degrees Celsius. For days, teams on Earth sent commands, waited and analysed the telemetry, their hearts pounding with every signal, confirming a motor had turned, a latch had released, a layer had tightened. It was an agonisingly slow process, a masterpiece of remote patience and precision. A single snag, a single tear, and the entire mission would be compromised, its golden eye blinded by its own heat. Then after the shield was in place came the moment of optical genesis. The magnificent primary mirror, a breathtaking mosaic of 18 gold-coated beryllium hexagons, had to unfold from its launch configuration. 2 side wings, each holding 3 mirror segments, swung into place, clicking into their final positions with microscopic accuracy. The secondary mirror, perched on a delicate-looking but incredibly rigid tripod, extended out to its precise focal point. The telescope for the first time began to assume its final iconic form. It was no longer just cargo, it was an eye. A vast golden honeycombed eye now open and staring into the void. But it was still blind. The 18 individual segments, beautiful as they were, acted as 18 separate small telescopes, each producing its own blurry image. The next phase was one of almost inconceivable finesse, the alignment. Over several months, tiny, powerful motors on the back of each segment began to move them in increments smaller than the width of a virus. They tilted, shifted and flexed, nudged by commands from Earth, all with the goal of making 18 mirrors act as one single, perfect monolithic reflector, a flawless parabolic surface 6.5 meters across. Scientists watched as the initial images from a target star, a chaotic spray of 18 blurry dots, were slowly, painstakingly coaxed into alignment. The dots moved closer, began to overlap, and then in a moment of sublime triumph they merged into a single breathtakingly sharp point of light, adorned with the telescope's signature 6-pointed diffraction spikes. The eye was now focused. The world's scientific community breathed a collective sigh of relief that was decades in the making. The instrument worked. It was more powerful, more sensitive, and more perfect than they had dared to dream. The time machine was assembled, its engine was running, and its lens was sharp. Now all that was left was to point it at the beginning of time. The first target for this revolutionary observatory was chosen with a profound sense of history. Just as Hubble had done with its legendary deep fields, JWST was tasked to stare for days on end at a patch of sky that appeared to all other telescopes utterly profoundly empty. A tiny sliver of the cosmos no bigger than a grain of sand held at arm's length. This is where the deepest secrets hide. In the darkness between the familiar stars in the voids that punctuate our night sky lies the portal to the most distant past. The telescope settled on its target, its instruments cooled to their operational temperature of minus 233 degrees Celsius, and then it simply began to wait. Patiently, the great golden eye began to drink in the ghostlight from the universe's edge. One by one, ancient photons, which had been travelling unimpeded through expanding space for over 13.5 billion years, ended their immense journey on the cold, sensitive surface of JWST's detectors. Each photon was a messenger from a lost epoch, a single word in a story that had never before been read. The exposure continued hour after hour, day after day. The data streamed back to Earth, a torrent of numbers and signals, which powerful computers began to translate into an image. Across the globe, astronomers and cosmologists waited, their careers and theories hanging in the balance. They thought they knew what they were going to see. Decades of cosmological modelling built upon the solid foundations of Einstein's relativity and our understanding of particle physics had made very specific predictions. They expected to see the first galaxies as they should be small, faint, clumpy, and misshapen. They would be the cosmic seeds, the struggling embers in the dying gloom of the Dark Ages, just beginning the long, slow process of gravitational assembly. These nascent structures, theorists argued, would be little more than fragile collections of the very first stars, wispy, tentative protogalaxies that would take billions of years to merge and grow into the grand spirals and ellipticals we see in the universe today. The models were elegant, logical, and universally accepted. They were the bedrock of modern cosmology. Then the image was released, and the bedrock of modern cosmology was shattered into a million pieces. The first thing that struck everyone was the sheer, overwhelming beauty. It was a treasure chest of light overflowing with galaxies of every shape, colour and size, but as scientists zoomed in as they looked past the familiar majestic spirals in the foreground, their beauty gave way to a creeping, profound sense of shock. They were looking for faint reddish smudges at the limits of vision. Instead, what they saw deep in the background of the image at the very edge of cosmic history was completely and utterly wrong. The most distant galaxies, the children of the dawn existing just 300 or 400 million years after the Big Bang, were not small, faint, or clumpy. They were astonishingly bright. They were shockingly massive, and there were far, far too many of them. It was as if you had travelled back in time to watch the very first multicelled organisms emerge from the primordial soup, only to find fully grown, complex animals already walking on the land. The universe, it seemed, had learned to build huge, brilliant, well-structured galaxies in a fraction of the time anyone had thought possible. These were not the predicted cosmic seeds. They were already towering celestial redwoods. In control rooms and university offices there was a stunned silence, followed by a frantic rush to check the data. Could the calibration be wrong? Could these be closer objects masquerading as distant ones? Was there some fundamental error in their understanding of the telescope itself? The initial reaction was denial. This simply couldn't be right. The established peer-reviewed Nobel Prize-winning models of cosmic evolution absolutely forbade the existence of such mature galaxies at such an impossibly early time. It was like finding a Roman skyscraper in the ruins of a Stone Age village. The timeline was broken. To confirm the heresy, astronomers turned to Webb's other superpower spectroscopy. An image can tell you what something looks like, but a spectrum tells you what it is. By splitting the light from these impossibly bright early galaxies into its constituent colours, like a prism, they could measure their properties with undeniable precision. Most importantly, they could measure their redshift. Redshift is the cosmic yardstick, the stretching of light to longer, redder wavelengths as the universe itself expands. The greater the redshift, the more the light is stretched, meaning the farther away the object is and the further back in time we are seeing it. The predictions were that the very first detectable galaxies might appear at a redshift of around 10, corresponding to about 480 million years after the Big Bang. The spectroscopic data that came back from Webb was unambiguous, and it was devastating to the old theories. One galaxy named Glass Z13 was confirmed at a redshift of 13.1. We were seeing it not 480 million years, but just 330 million years after the beginning of everything. Others soon followed, pushing the boundary even closer to the dawn. And these were not faint smudges. They were ablaze with the light of millions of young hot massive stars. Some appeared to have already assembled into rotating disk structures, a level of organisation that was supposed to take billions of years to develop. They were pumping out stars at a ferocious rate, far faster than the gentle, slow-starting process the models had described. The universe had quite clearly been in a hurry. The period of cosmic dawn wasn't the slow, gentle flicker of a candle being lit in the dark. It was a raging, galaxy-building inferno ignited almost immediately after the lights went out at the end of the Dark Ages. This single breathtaking revelation has thrown cosmology into a state of thrilling chaos. The architectural blueprints we had drawn for the universe were fundamentally flawed. Something is missing from our story of creation. How could galaxies grow so big so fast? Did the first stars form even earlier than we thought, providing the seeds for rapid growth? Does star formation itself work differently in the pristine hydrogen-filled environment of the early cosmos? Or does this point to something deeper, something more profound about the very fabric of reality? Could our theories about dark matter, the invisible gravitational scaffolding upon which galaxies are built, be wrong? Perhaps it is not as cold and slow-moving as we believe, allowing it to clump together much more quickly and efficiently in the primordial furnace. The James Webb Space Telescope was built to answer the question of how the first galaxies formed. Instead, in its very first dispatches from the dawn of time, it has taken that question and transformed it into a far more tantalizing and far more difficult mystery. It has shown us that the story we were telling ourselves was far too simple, too neat, too slow. The opening act of our universe was not a quiet prelude. It was a spectacular, brilliant, and inexplicably rapid explosion of creation, the details of which we are only now in our breathtaking ignorance beginning to unravel. For a fleeting, glorious moment, the universe made sense. The images that had cascaded down from the telescope's golden eye were a triumph, a confirmation of a half-century of theoretical work. There they were, the faint red whispers of the first galaxies, just as we had predicted. But as the initial wave of elation subsided, a deeper, more unsettling feeling began to ripple through the global community of astronomers. A quiet murmur of disbelief that soon grew into a chorus of profound confusion. Because while we had found the first galaxies, they were not the faint, fragile seedlings we had expected to see. What JWST had unveiled was something else entirely. Something impossible. Something that threatens to shatter our entire understanding of how the cosmos came to be. The ghosts in the machine were not just ghosts, they were giants, and they were staring back at us from a time when they had no right to exist. This is the intellectual crisis that followed the celebration, the unnerving silence after the symphony's crescendo. We are now forced to confront a paradox that strikes at the very heart of modern cosmology, the too big, too soon problem. The grand cosmic blueprint, meticulously drawn over decades of observation and calculation, described a universe built slowly, methodically from the bottom up. The prevailing lambda-cold dark matter model, our standard model of the universe, was unambiguous on this point. It told a story of patient hierarchical construction. After the Big Bang, the universe was an almost perfectly smooth, hot, dense soup of particles and energy. Tiny quantum fluctuations in that primordial state, infinitesimally small variations in density, were the seeds of everything to come. We've seen the imprint of these seeds with breathtaking precision in the cosmic microwave background, the afterglow of creation itself. According to our story, these slightly denser regions contained more gravity. Over hundreds of millions of years, they would act as cosmic anchors, patiently pulling in the mysterious invisible substance we call dark matter. This dark matter, making up over 80% of all matter in the cosmos, would form the underlying architecture of existence. It would coalesce into small invisible clouds or halos, the gravitational scaffolding upon which everything else would be built. Only then, once these dark matter structures were in place, would ordinary matter, the hydrogen and helium gas forged in the Big Bang, begin to feel their pull. Gas would slowly trickle in, cooling, condensing, and eventually under its own weight collapsing to ignite the first stars. These were the predicted proto-galaxies, small, scrappy and disorganized collections of stars destined to merge and grow over billions of years into the majestic spirals and ellipticals we see today. It was an elegant, logical and powerfully predictive narrative, and it is a narrative that now appears to be fundamentally and perhaps spectacularly wrong. The galaxies JWST has shown us from just 300 million years after the Big Bang are not small. They are not scrappy. Some of them appear to be as massive as our own Milky Way is today, a structure that took 13.5 billion years to assemble. This is not a minor discrepancy. This is like finding a fully grown ancient redwood tree in a greenhouse where you had planted a seed only yesterday. The timeline simply does not compute. The very first question this forces us to ask is a deeply unsettling one. Did we misunderstand the seeds themselves? The density fluctuations seen in the cosmic microwave background are the starting conditions for the entire cosmic simulation. If those initial seeds were somehow larger, more pronounced than we measured, then perhaps gravity had a head start. But our measurements of the CMB are among the most precise in all of science. To suggest they are that wrong would be to unravel the tapestry of cosmology all the way back to its origin point. So if the seeds were right, perhaps the problem lies with the scaffolding. Our models treat dark matter as cold, meaning its particles were moving slowly in the early universe, allowing them to clump together easily under gravity's influence. This coldness is what dictates the bottom-up hierarchical assembly. Small halos form first, then merge into bigger ones. But what if dark matter wasn't so cold? What if it possessed some property, some unknown interaction that allowed it to coalesce far more rapidly in the dense environment of the infant cosmos? We are forced to consider that this invisible substance, this gravitational ghost that holds galaxies together, might have a richer, more complex nature than we ever imagined. The neat, simple assumptions that made our models work so well for the later universe may be failing us here in the frantic crucible of the beginning. The smooth, predictable process of gravitational collapse we programmed into our simulations might be a pale imitation of a far more violent, efficient and rapid reality. The universe, it seems, was in a hurry, and the problem only deepens when we move beyond the dark matter skeleton and consider the flesh, the ordinary baryonic matter that makes up the stars, the planets and us. Even if by some unknown mechanism a massive dark matter halo could form with impossible speed, it still needs to capture an immense reservoir of hydrogen and helium gas to build a galaxy. This process was also thought to be a bottleneck. The early universe was expanding rapidly, pulling everything apart. For gas to overcome that expansion and fall into a dark matter halo, it had to travel along the faint thread-like filaments of the cosmic web, a slow and steady process of accretion. The galaxies revealed by JWST, however, don't look like they were fed by a delicate cosmic drip. They look like they feasted. They somehow managed to gather colossal amounts of fuel in a cosmic nanosecond, defying the very expansion of space that should have kept their larders bare. This leads us to the engine of the galaxy itself, star formation. Let us assume for a moment that a massive halo of dark matter did form, and that it did manage to capture a vast ocean of primordial gas. You still have to turn that gas into stars. And this is perhaps the most stubborn paradox of all. The process of star birth is notoriously inefficient and crucially self-regulating. The very first stars to ignite the hypothetical population 3 stars were thought to be monsters hundreds of times the mass of our Sun. They would have burned with an unimaginable ferocity, bathing their surroundings in torrents of high-energy radiation. And they would have died young, exploding as cataclysmic supernovae that would have blasted through their host proto-galaxies like a celestial blowtorch. This process, known as feedback, is a fundamental component of every model of galaxy formation. The first generation of stars should by their very nature have slammed the brakes on any subsequent star formation. Their explosive deaths should have heated and ejected the surrounding gas, effectively starving the galaxy of the fuel needed to make a second generation. This is the universe's natural thermostat, preventing everything from turning into stars all at once. It's the reason star formation is a slow, steady burn over cosmic history, not a single explosive conflagration. Yet the galaxies JWST is showing us look like they have somehow disabled this thermostat. They are not just massive, they are luminous, blazing with the light of billions of young stars. Their star formation rates the pace at which they convert gas into suns are hundreds, even thousands of times higher than what we see in the local universe. Their engines are redlining, running at a pace that our physics says should have blown them apart before they ever had a chance to grow. It's as if we've found an entire ecosystem of organisms that defy the very concept of metabolism, growing to colossal sizes without any apparent source of energy or any mechanism to control their growth. But the telescope's instruments' marvels of spectroscopic precision give us more than just size and brightness. They give us a way to perform cosmic archaeology. By splitting the faint light from these galaxies into its constituent rainbow of colours, JWST can read their chemical barcodes, and this is where the mystery transforms into a seemingly insurmountable contradiction. The Big Bang created only the lightest elements, hydrogen, helium, and a whisper of lithium. Every other element on the periodic table, the carbon in our bodies, the oxygen we breathe, the silicon in the rocks beneath our feet, was forged in the nuclear furnace of a star's core and scattered into space when that star died. In astronomical terms, all elements heavier than helium are simply called metals. The very first generation of stars therefore should have been metal-free pristine objects of pure hydrogen and helium. The galaxies they formed should have likewise been chemically primitive. We expected to look back with JWST and find this primordial state of matter, to see the universe before it had been enriched by the life and death of stars. But that is not what we are finding. When we analyse the light from these galaxies at 300 million years cosmic time, we find the unmistakable spectral fingerprints of carbon, of nitrogen, of oxygen, and neon. These are not pristine first-light objects. They are already polluted, already enriched with the ashes of a previous generation of stars. This single, staggering fact compresses the cosmic timeline to an almost nonsensical degree. It means that within the first few 100 million years, the universe had to form a first generation of stars. Those stars had to live their entire lives, explode as supernovae, and scatter their newly forged elements across space. Then that enriched material had to cool, coalesce, and collapse again to form the second generation of stars that we are now observing with JWST. An entire cycle of cosmic life and death. A process we thought took 1 billion years or more seems to have been completed in a fraction of that time. These are not baby galaxies. They are at best adolescent galaxies with a history written in their chemistry, existing at a time when we expected to find only cosmic infants. They are too big, they formed too soon, and they are far too chemically mature. Every single piece of evidence points to a process of cosmic evolution that was radically accelerated, running on a clock that seems to be ticking far faster than our own. The universe was not just in a hurry. It was operating at a pace that borders on the magical, defying the speed limits we thought were hard-coded into the laws of physics. And as if to mock our confusion, the universe presented us with an even more extreme version of this paradox, because it wasn't just galaxies that were growing too fast. Lurking in their cores was an even greater monster. The standard model of cosmology tells us that galaxies and the supermassive black holes at their centres grow up together in a delicate symbiotic dance. A black hole grows by feeding on the gas and stars of its host galaxy, and the energy released by this feeding frenzy in turn regulates the growth of the galaxy itself. This coevolution is a cornerstone of our understanding, but it is once again a slow process. To grow a black hole to 1 billion times the mass of our Sun should take billions of years of steady feeding and violent mergers. Yet JWST is discovering quasars, blazing galactic cores powered by actively feeding supermassive black holes, each 1 billion solar masses or more, shining brightly just a few hundred million years after the Big Bang. This is not just a redwood in a greenhouse. This is finding a finished Manhattan skyscraper on a construction site a week after groundbreaking. It is a physical impossibility under our current assumptions. There simply is not enough time. There isn't enough time for a stellar mass black hole to form from a dying star and then feed fast enough to reach that size. The very act of feeding at such a rate, the so-called Eddington limit, should generate so much radiation pressure that it would blow its own fuel away. How then do you build a monster in the dark when the very act of eating turns on a light so bright it clears the table? The existence of these objects demands a different origin story. Perhaps they weren't built up from stellar seeds at all. Perhaps they were born colossal. Theories of direct collapse black holes posit that in the unique conditions of the early universe, a vast cloud of primordial gas could have collapsed directly into a black hole of 100,000 solar masses, skipping the star phase entirely. It's a compelling idea, but one that requires a perfect storm of conditions that should be incredibly rare. Or perhaps the seeds were there from the very beginning. An even more exotic theory, whispers of primordial black holes not forged in dying stars but created in the first fraction of a second, after the Big Bang itself squeezed into existence by the immense pressures of creation. Could these ancient relics have served as the gravitational anchors around which the first galaxies coalesced with such astonishing speed? It is a tantalizing, almost frightening possibility. To accept it means accepting that the seeds of cosmic structure were not just tiny ripples of density, but massive invisible singularities waiting in the dark for the universe to catch up to them. We stand at a genuine precipice. The data streaming down from our golden eye in space is not refining our model of the universe, it is breaking it. The elegant clockwork cosmos that we were so confident in has been replaced by a chaotic, violent and hyper-efficient version that churns out structure at a rate we can't explain. The pillars of our understanding, the nature of dark matter, the pace of gravitational collapse, the efficiency of star formation, the timeline of chemical enrichment, the growth of black holes are not just being questioned, they are crumbling under the weight of observation. This is not a moment of failure, but a moment of profound, exhilarating opportunity. For the first time in a generation, the map of the early universe is being completely redrawn. The story we thought we knew was just the prelude. And as we confront this beautiful impossible dawn, we are forced to ask a new set of questions, to entertain ideas once relegated to the fringes of science, and to search for a new physics that can explain the magnificent, baffling hurry the universe was in to become the home we know today. And so, with the cosmic rulebook torn to shreds, we find ourselves adrift. The elegant, carefully constructed timeline of the universe, a story we had told ourselves for decades now, lies in pieces shattered by the light of galaxies that have no right to exist. They are temporal paradoxes rendered in starlight and gas, their very presence a direct challenge to our understanding of cosmic law. The crisis isn't one of observation. The data pouring down from Webb is immaculate, its precision beyond question, its clarity a revelation. No, the crisis is one of imagination. Our theories, our sophisticated computer simulations that took years to build, are suddenly exposed as tragically incomplete, like trying to predict a hurricane with a barometer that only measures gentle breezes. Faced with this beautiful, confounding evidence, a schism has opened in the halls of science. On one side, the comfort of established physics. On the other, the radical possibilities demanded by these new photons. The scientific community, a global collective of brilliant minds, has turned its full attention to this singular, monumental problem. This is not a moment of failure, but a moment of profound opportunity, the sound of a locked door finally being kicked open. In conference rooms on whiteboards and in the silent churning of supercomputers, a new story of creation is being written not from a single pen, but from the frantic, inspired work of thousands. We are witnessing in real time the chaotic, exhilarating process of a paradigm shift. The central question has been thrown into the sharpest possible relief. If galaxies formed that fast, if they grew that large, that quickly, what fundamental ingredient did our cosmic recipe leave out? One of the most audacious new ideas takes us back, all the way back before the first star, before the first atom, to the universe's own source code. For years, our map of the infant cosmos, the cosmic microwave background, has been our most reliable guide to the initial state of everything. It shows us a universe of almost impossible uniformity, a smooth primordial soup where matter was spread with incredible evenness. The variations, the tiny ripples in temperature that would one day become galaxies, were measured to be minuscule, just 1 part in 100,000. Our models of cosmic evolution were built upon this foundation of smoothness, this assumption of a gentle, slow start. This gentle topography meant that gravity had a long, arduous task ahead of it. It had to patiently pull together these slightly denser regions over hundreds of millions of years, a slow gravitational creep that eventually painstakingly built the first star clusters. But what if that map, as precise as it is, was hiding something in plain sight? What if the smoothness was an illusion of scale? Webb's impossible galaxies suggest that gravity didn't have to work so hard. They behave as if they had a massive head start. This has forced theorists to reconsider the very initial conditions of the universe. Perhaps the original density fluctuations weren't so gentle after all. Imagine the CMB not as a placid lake with tiny ripples, but as a vast ocean where hidden beneath the surface were powerful localized currents and deep unseen valleys. In this revised picture, the universe wasn't born uniformly smooth, but was instead seeded with pockets of significantly higher density. These were not just slight overdensities, they were cosmic lottery wins regions blessed with a gravitational advantage from the very first moments of time. While most of the universe began a slow, gradual process of formation, these privileged zones were already primed for collapse. Gravity here wasn't gently coaxing matter together. It was a ferocious, inescapable force acting on an abundant local supply of fuel. The dark matter in these pockets would have formed a much denser, more potent scaffolding, creating gravitational wells so deep that gas didn't just trickle in, it cascaded. It was a cosmic flash flood, a runaway process of accumulation. This lumpier early universe would resolve Webb's paradox almost instantly. Galaxies wouldn't need hundreds of millions of years to assemble piece by piece. They could have sprung into existence with shocking speed, their foundations laid not by slow accretion, but by a dramatic foundational collapse. It changes our entire perception of the cosmic dawn. It was not a uniform, gentle sunrise spreading evenly across the horizon, but a violent, explosive series of popping flashbulbs with brilliant islands of creation igniting in a sea of overwhelming darkness. This idea is profound because it means Webb is not just seeing the first galaxies, it is peering behind that curtain, providing indirect clues about the physics that govern the universe in its first fractions of a second. The structure of a galaxy burning 400 million years after the Big Bang is telling us something fundamental about the nature of quantum fluctuations that were inflated to cosmic scales in the moment of inflation itself. We're connecting the largest structures we can see with the smallest, most ephemeral events at the dawn of time. The challenge now is to find the smoking gun. If this hypothesis is true, we should see evidence of this lumpiness elsewhere. The distribution of these early galaxies shouldn't be random. They should be clustered, tracing the outlines of these primordial high-density regions, like foam gathering on the crests of invisible waves in space-time. Every new galaxy Webb discovers becomes another data point in a vast exercise of cosmic cartography, mapping not just space but the very texture of the beginning. But perhaps the problem isn't with the cosmic blueprints. Perhaps the issue lies with the builders themselves. A second equally powerful explanation turns the spotlight away from gravity and onto the enigmatic first generation of stars, population 3. For decades, these stars have been the titans of cosmic lore, mythical beasts forged from pure hydrogen and helium, the raw material of the Big Bang. Our models had painted a picture of them as impossibly massive, hundreds of times the mass of our Sun, living short, incandescent lives before dying in cataclysmic explosions that seeded the universe with the first heavy elements. We believed we understood them, at least in theory. We calculated their temperatures, their brightness, their impact. And from these calculations, we derived a budget for reionization, the epic process where the light from these first stars burned away, the neutral hydrogen fog that had filled the universe for eons. Our model suggested this was a gradual, protracted affair. The first stars were powerful, but the darkness was vast. It would take time for their collective light to carve out bubbles of transparency, for those bubbles to grow and merge, and for the entire cosmos to become clear. Webb's observations have thrown this entire budget into disarray. The universe appears to have cleared up far too quickly. The galaxies it sees are not shrouded in a thick light-scattering fog. They are sitting in vast regions of space that are already transparent. This implies that the process of reionization was not a slow burn but a wildfire. Something or someone was fantastically more efficient at this task than we ever predicted. The new hypothesis is that we have fundamentally underestimated the power of population 3 stars. What if they were not just big, but were true monsters of the cosmos celestial engines of terrifying efficiency? Computer simulations are now being recalibrated, pushed to new extremes. Scientists are exploring scenarios where the initial mass function, the statistical distribution of stellar masses, was radically different in the early universe. Instead of producing a mix of large and smaller stars, what if the primordial clouds of hydrogen and helium almost exclusively formed colossal giants? Top-heavy distribution like this would change everything. A single star 300 times the mass of our Sun doesn't just shine 300 times brighter. Its luminosity increases exponentially with its mass. Such a star would be millions of times brighter than the Sun, a celestial blowtorch pumping out a torrent of high-energy, ultraviolet photons, the very radiation needed to strip electrons from hydrogen atoms and reionize the cosmos. A single cluster of such stars could do the work that we once thought required an entire galaxy. They would have burned with an alien intensity, their surfaces so hot that their light was a far more effective tool for clearing the cosmic fog. Their lives would be fleeting, a mere million years of furious light, but their impact would be permanent. They would be cosmic catalysts, jump-starting the entire process of cosmic evolution. The galaxies Webb is seeing might seem mature not because they are old, but because they were born into an environment that was violently and rapidly transformed by these short-lived, hyper-efficient stellar ancestors. They are like trees growing in soil that has been aggressively fertilized, experiencing a burst of growth that seems to defy the normal passage of time. Furthermore, their deaths would be as consequential as their lives. When these supergiants exploded, they wouldn't just scatter a dusting of new elements. They would unleash shockwaves of unimaginable power. These shockwaves would compress the surrounding gas, triggering furious new bursts of star formation in a self-perpetuating cycle of creation. Starbirth would beget more starbirth, a chain reaction that could assemble a complex, thriving galaxy in a fraction of the time our old models allowed. This theory places the first stars at the very center of the drama. They are no longer just the first lights, but the prime movers, the agents of accelerated change who engineered the environment for their own successors. The search is now on for their faint chemical fingerprints in the atmospheres of the later stars, or for the telltale signs of their explosive deaths in the distant universe. Webb is not just a galaxy finder, it is a ghost hunter searching for the spectres of these long-dead titans. Yet there is a third path, a darker and perhaps more profound possibility. It whispers that the accelerated timeline of the cosmos was driven not by the brilliance of stars, but by the insatiable hunger of an invisible monster lurking at the heart of it all. This theory shifts our focus from the bright shining matter we can see, and directs it towards the universe's masters of gravity black holes. In our traditional story of galaxy formation, the bottom-up model black holes were an afterthought. They were born from the collapse of massive stars and grew slowly over billions of years, merging and feeding, eventually becoming the supermassive giants we see in the center of galaxies today. In this picture, the galaxy always comes first. The black hole is a consequence of the galaxy's evolution. But the sheer size and structure of Webb's early galaxies hint at a process that is far too organized, far too rapid, for such a chaotic, piecemeal assembly. They look as if they were built with a purpose, a design as if they formed around a pre-existing cosmic anchor. This has given rise to a revolutionary, almost heretical idea that the supermassive black holes came first. This is the top-down model of cosmic construction, and it proposes the existence of direct collapse black holes. These are not the remnants of dead stars. They are primordial behemoths born directly out of the collapse of vast pristine clouds of hydrogen and helium in the very early universe. Imagine a cloud of gas 100,000 times the mass of the Sun. In the standard model, such a cloud would fragment, forming a brilliant star cluster. But under certain very specific conditions, if the gas is exceptionally pure and hot, preventing it from cooling and fragmenting, the entire cloud can collapse in on itself in a single catastrophic event, bypassing the stellar phase entirely. The result is not a star, but a black hole seed already tens of thousands, or even hundreds of thousands of times the mass of our Sun. It would be a monster from birth. Such an object would fundamentally rewrite the rules of galaxy formation. It would not be a passive occupant of a galactic core. It would be the galaxy's creator, its engine, its heart. Its immense gravitational pull would act as a cosmic whirlpool, a gravitational command center from which the rest of the galaxy would be built. It would pull in gas from millions of light years away, funneling it into a dense swirling accretion disk. The friction and pressure in this disk would heat the gas to millions of degrees, causing it to shine with a brilliance that could outshine an entire galaxy of stars. This is a quasar, and we have seen them in the distant universe. But this new theory suggests they were the sparks, not just the lighthouses. More importantly, not all the gas would fall into the black hole. Much of it would be compressed in the surrounding region, igniting into a spectacular concentrated burst of star formation. The black hole would be both a destroyer and a creator, its feeding frenzy directly triggering the birth of its host galaxy around it. A galaxy wouldn't have to slowly assemble from countless smaller mergers. It would be born whole in a halo of furious starbirth, orchestrated by the gravitational field of its central engine. This black hole first model elegantly explains the uncanny maturity of Webb's discoveries. These galaxies look structured and massive because they were born that way, their growth supercharged from day one by a central shadowy architect. It suggests that the history of the universe is not just the history of stars and light, but a parallel hidden history of darkness and gravity. The cosmic web we see, the intricate tapestry of galaxies, might just be the visible manifestation of an underlying invisible scaffolding of massive black holes. Suddenly we are forced to see the universe in a new light, or rather a new darkness. We have to ask, are we seeing galaxies that just happen to contain black holes, or are we seeing the luminous stellar nurseries that were purposefully constructed by them? Each of these competing visions are Lumpier. Beginning supercharged stellar ancestors or black hole architects is a radical departure from the cosmology of yesterday. They are not small adjustments to the old story. They are entirely new chapters, each with profound implications for the nature of our universe, and they are not mutually exclusive. The truth, when we finally uncover it, may be a complex symphony of all three. Perhaps the universe was indeed born lumpier, and in those densest primordial pockets, population 3 monsters ignited only to collapse into the direct collapse black holes that then orchestrated the building of the first grand galactic structures. The clean, simple lines of our previous theories are dissolving into a far more intricate, interconnected, and ultimately more fascinating picture. Webb has not given us the answer. Instead, it has given us something far more valuable. It has given us the right questions to ask. And with every new observation, with every distant galaxy pulled from the darkness, we gather another clue, slowly resolving the central conflict, piecing together the true story of how, against all odds, our universe finally brilliantly and violently emerged from the dark. And so we find ourselves standing on a shore we never expected to reach, the echo of shattered paradigms still ringing in our ears. For generations we gazed across a vast dark ocean of time, an abyss of 400 million years separating us from the universe's beginning. It was a void in our knowledge, a chapter torn from the cosmic story, populated only by the ghosts of elegant theories and powerful simulations. We called it the Dark Ages, a name that spoke of our own blindness more than any inherent truth of the universe itself. We imagined a slow tentative dawn, a gradual sputtering of light as the first lonely stars timidly pushed back against an infinite blackness. We built our grand cosmological cathedral on this foundation of assumption, a story of slow hierarchical growth where tiny seeds of matter patiently gathered over immense eons to form the first fragile protogalaxies. It was a beautiful, logical, and deeply sensible story, and as the James Webb Space Telescope has now shown us in its most crucial details, it appears to be profoundly wrong. The journey we have taken together through the spectral fingerprints of hydrogen and across redshift chasms of 13.5 billion years was not a journey into a quiet gestating nursery. It was a plunge into a cosmic firestorm. The universe did not awaken with a gentle whisper. It appears to have been born screaming alight with a ferocity that has rocked the very foundations of cosmology. That darkness we envisioned was not empty, but pregnant with possibility, and the dawn that followed was not a tentative sunrise, but a blinding flash, an explosive efflorescence of structure and complexity. What JWST has done is more than just deliver new data points. It has forced us to confront the humbling reality that our imagination, for all its power, was far too conservative. It has taken a story we thought we knew and turned the final page only to reveal it was merely the preface to a far grander, wilder, and more mysterious epic than we ever dared to conceive. We have in the space of a few short years gone from being blind to seeing with a clarity that is both exhilarating and terrifying. Exhilarating because the universe is proving to be richer and more creative than our models allowed, and terrifying because we the storytellers must now find the language and the physics to explain it. Our entire conception of cosmic evolution was built upon a simple, elegant idea that things start small and grow big over time. Galaxies, like great cities, were thought to begin as small hamlets, gradually merging and accreting over billions of years to become the sprawling spiral and elliptical metropolises we see today. This bottom-up model was the central pillar of our understanding, a gravitational symphony conducted by the slow, inexorable pull of dark matter. JWST was meant to find the first faint notes of that symphony, to spot the tiny disorganized clumps of stars and gas that our theories predicted would litter the cosmic dawn. Instead, it found orchestras already in full swing. In the deepest, reddest patches of the sky where we expected cosmic villages, we found celestial cities, galaxies like JWST Z13E0, blazing with the light of 1 billion suns just 320 million years after the Big Bang. These were not the primordial chemically simple assemblies we anticipated. Their light broken down by Webb's exquisite spectrographs told a story of shocking maturity. We saw the distinct spectral signatures of oxygen, of neon, even of carbon elements forged in the hearts of massive stars that must have already lived, died, and seeded the cosmos with their ashes. This chemical enrichment, this celestial alchemy, was supposed to take time, requiring multiple generations of stars to build up these heavier elements. Yet here they were in abundance when the universe was a mere 2% of its current age. It's like exploring a supposedly uninhabited island and finding the ruins of a sophisticated, multi-generational civilization. The timeline simply doesn't seem to add up. The galaxies themselves displayed a level of organization that was startling. We saw evidence of rotating galactic disks, stable structures that, according to our models, should have taken 1 billion years or more to settle. They were gravitational gyroscopes already spinning with an impossible poise in what was supposed to be a chaotic, violent era of constant collisions. And inside these impossibly advanced galaxies we found monsters. Our theories of black hole formation were also built on a model of patience. A massive star collapses, forming a stellar mass black hole perhaps a few dozen times the mass of our Sun. This seed then slowly, painstakingly feeds on gas, and merges with other black holes growing over cosmic ages into the supermassive behemoths that anchor galaxies like our own Milky Way. The process was thought to be efficient but not miraculous. JWST, however, has shown us quasars' blazing galactic cores powered by feeding black holes shining with the light of 100 trillion suns from an epoch when the universe was only 600 or 700 million years old. The black holes driving these cosmic lighthouses were not a few million but over 1 billion times the mass of our Sun. To grow that large, that fast from a conventional stellar seed is not just difficult. It may be physically impossible. It would require the black hole to be feeding at a rate so extreme, so far beyond the theoretical limits of physics, that it would tear itself apart. It's a cosmic paradox of epic proportions. We are staring at objects that by our best understanding simply should not exist. The evidence is unimpeachable, etched into the stretched wavelengths of ancient light, forcing us to question everything we thought we knew about the universe's most massive objects. Did the universe have a way to create heavy seeds, black holes born directly from the collapse of colossal primordial gas clouds, weighing in at hundreds of thousands of solar masses from the very beginning? Such an idea, once a fringe theory, is now being brought into the mainstream, driven by the sheer impossibility of the alternative. JWST has not just added detail to our picture of the early universe, it has thrown the entire canvas into question. It has revealed a universe that was seemingly born in a hurry, one that built complex, massive and chemically rich structures, with an efficiency that our current cosmological model, lambda CDM, struggles to explain. The cosmic dawn was less a dawn and more a sudden galaxy-rich noon. The 400 million year gap in our knowledge has been filled, but not with the comfortable, predictable story we wrote for ourselves. It has been filled with a tale of impossible speed, precocious growth and monstrous appetites that defies simple explanation. The age of comfortable certainty is over. A new age of profound mystery has just begun. For every question Webb has answered, it seems to have sculpted a dozen more, each deeper and more fundamental than the last. The observations are not just tweaking the dials of our models, they are pointing to a potential fault line in our understanding of the cosmos itself. If galaxies grew so massive so quickly, does this mean the process of galaxy formation is far more efficient than we believed? Or does it hint at something more fundamental about the ingredients of the universe? Perhaps the behavior of dark matter, the invisible scaffolding upon which galaxies are built, is different in the dense early universe. Does it clump together more effectively? Does it possess properties we have yet to discover which accelerate the initial collapse of gas and turbocharged star formation? These are no longer mere academic questions. They strike at the heart of the lambda CDM model, our standard model of cosmology that has for decades successfully explained the large-scale structure of the universe. We now face the tantalizing and unsettling possibility that this model, while correct on broad strokes, is missing a crucial ingredient, a piece of physics that only becomes apparent in the extreme conditions of the cosmic dawn. We are like cartographers who have mapped the continents of the Earth with great success, only to find an entirely new, unsuspected landmass. The challenge is not just to map it, but to understand how it changes our entire view of the world. And what of those monstrous black holes? The heavy seed model is a compelling solution, but it opens its own Pandora's box of questions. What were the precise conditions that allowed such enormous objects to collapse directly out of primordial gas? Did this process only happen in that very first cosmic chapter, a unique feature of a younger, denser, purer universe? If so, these first quasars are not just the ancestors of modern galactic nuclei. They are fossils of a completely alien mode of cosmic creation, a process lost to time. Furthermore, how did these behemoths influence their surroundings? We once saw galaxies as the dominant partners slowly feeding their central black holes. Now we must entertain the opposite, that these gargantuan black holes formed first, or concurrently acting as the gravitational anchors, the cosmic seeds around which the first galaxies themselves coalesced. Did the universe build galaxies to house its black holes, or did it build black holes inside its galaxies? This chicken and egg problem has been thrown into stark relief, reversing our entire perspective on the co-evolution of the universe's larger structures. Then there is the question of the first stars, the enigmatic population 3 stars. We built JWST in part to find them these mythical first points of light, forged from pure hydrogen and helium in the moments after the Big Bang. They were predicted to be hundreds of times more massive than our Sun, living short, violent lives and dying in spectacular explosions. Yet for all of Webb's power, we have not found definitive direct evidence of them. Instead, we find galaxies already polluted with the chemical ashes of their existence. Were they so massive and short-lived that they vanished almost instantly? Did they form in dense clusters whose collective glow is what we are now seeing as the cause of these first galaxies, their individual identities forever lost in a crowd? The absence of evidence is not evidence of absence, but it is a profound and tantalizing clue. It suggests the transition from that first pure generation of stars to the second chemically enriched generation was brutally swift, a cosmic baton pass that happened in the blink of a galactic eye. We find ourselves in a remarkable position. We have pushed back the frontier of observation so far and so fast that we have in a sense outrun our theories. The data streaming back from its orbit at Lagrange Point 2 is no longer just confirming our predictions. It is now leading the dance, challenging theorists and simulators to build a new framework that can account for this wild, impetuous youth of our universe. The mystery of the first 400 million years has not been solved. It has been replaced by a more complex, more nuanced, and far more exciting set of puzzles. We have traded ignorance for paradox, and in science, paradox is the engine of all true progress. This new universe, dazzling and perplexing, is not a final destination. It is a staging ground for the next great age of discovery. The James Webb Space Telescope is not a lone sentinel. It is the vanguard of a new coordinated assault on the cosmic frontier. Its mission to chart these primordial galaxies continues. With every passing month, its deep field observations go deeper, spending hundreds of hours staring at single tiny patches of sky, accumulating photons that have travelled for over 13 billion years to build up images of unprecedented depth and clarity. Each new image peels back another layer, revealing even fainter, even younger structures, pushing ever closer to that theoretical first-light horizon. But Webb's true power in this next chapter will be its synergy with a new generation of behemoths taking shape here on Earth. On the peaks of the Chilean Andes and the summit of Mauna Kea, we are building the largest optical telescopes in human history. The Giant Magellan Telescope, the 30-metre telescope, and the European Extremely Large Telescope. These are not competitors to Webb, they are essential partners. With mirrors stretching up to 39 metres across, they will have light-gathering power that dwarfs anything before them. While Webb, from its cold, stable perch in space, is the perfect instrument for finding the faintest, reddest candidates, these ground-based giants will be the ultimate analytical laboratories. Using advanced adaptive optics to cancel out the blurring effects of Earth's atmosphere, they will be able to lock onto the targets Webb discovers and dissect their light with a level of detail Webb cannot match. They will be able to probe the internal motions of these infant galaxies, mapping the velocities of their gas and stars to see if they are truly rotating disks or chaotic merging assemblies. They will perform ultra-high-resolution spectroscopy, allowing us to measure the abundances of different elements with exquisite precision testing for the unique chemical signatures predicted for the deaths of population 3 stars. It will be a cosmic conversation across millions of miles. Webb will point the way, saying, "Look here is something strange and unexpected." And from the mountaintops of Earth, our new eyes will stare back, responding, "We see it. And here is what it's made of, here is how it's moving, and here are the physical conditions inside it." This partnership between space and ground is the future of astronomy. But observation alone is not enough. The torrent of data from these new facilities requires an equal revolution in theory and simulation. On the world's most powerful supercomputers, cosmologists are now scrambling to build new models that can accommodate this impossibly rapid evolution. They are running vast digital universes, tweaking the fundamental parameters of dark matter, of star formation, efficiency, of black hole seeding mechanisms. They are testing radical new ideas, asking what if on a cosmic scale. What if the initial ripples of density from the Big Bang were larger than we thought? What if primordial magnetic fields played a role in accelerating gas collapse? Each simulation is a grand experiment, a universe in a box which can be run forward in time and compared to Webb's actual observations. When the simulation matches the reality, we will know we are on the right track. This iterative dance between observation theory and simulation is how we will slowly piece together the new story of our cosmic origins. It will be a story written in photons, tested in silicon, and ultimately understood by the human mind. The quest is no longer just to see the dawn, but to comprehend it. We began our journey seeking an origin story, a simple linear path from the fireball of creation to the world we know. We sought to connect the dots backward in time from our own Milky Way through the cosmic noon of star formation, across the long, quiet afternoon of the universe's expansion, all the way back to the first tentative glimmers of light in the morning mist. We believed it would be a story of patient, predictable emergence. Instead, we have found that the universe was born a prodigy. The light from these first galaxies, which has travelled across the entire expanse of space and time to fall upon Webb's golden mirror, is more than just a scientific curiosity. It is our ultimate ancestral light. In the spectral lines of carbon, oxygen and neon, in those impossibly distant galaxies, we see the raw materials from which we are made. The atoms forged in those first furious generations of stars were cast out into the intergalactic medium, becoming part of the great cosmic cycle of matter, eventually finding their way into a cloud of gas and dust that would, 10 billion years later, collapse to form our Sun, our Earth, and our bodies. When you look at these images from JWST, you're not looking at something alien and separate. You're looking at the very beginning of your own story. You're seeing the great-great-grandparent stars of our own galaxy, the cosmic crucible in which the elements of life were first forged. The questions JWST has raised of impossible speed of unexpected complexity are not just questions about astrophysics. They are questions about our own existence. The answers will tell us not only how the first galaxies formed, but how the universe became a place capable of supporting life. The journey into the dark is over, but the journey into the light and into understanding that light has just begun. It is a journey that reminds us that the universe is not only stranger than we imagine, but stranger than we can imagine, and that the greatest discoveries lie not in confirming what we know, but in having the courage to embrace the beauty of what we do not. The script is not yet written, the greatest chapters are still ahead, and the light is waiting.